All right, hello everyone. Quick July 10th update. I sent the LICOR unit back to LICOR because it was broken again. We have a potential loan replacement from New Mexico Tech on the way, as well as from Los Alamos, so hopefully we'll be able to get the data collection back up and running. The Picaro cooling system, thanks to the Pinterns for looking into that. I installed a vent to move the hot air out of the tented system. And there's a few different cooling systems we need to investigate further and build in order to keep the Picaro cool as we try and collect data during the hot months here. Majority of my time has been spent on writing the bench scale experiments in specific. Volumetric flow rate measurement is a focus. All the literature that I've seen, most of it at least, refers to the standards put forth by the EPA, and their recommended method for measuring volumetric flow rate is this pitot tube traverse using differential pressure pitot tubes to back calculate the velocity using these coefficients as well as temperature, pressure, and the density of the gas, or in this case the molecular weight. This presents a problem because not only do we not have pitot tubes, but we don't have a method for measuring all the constituents of the airflow stream, and that makes calculating the density impossible. And so what we wanted to do is be able to have a direct measurement just using an off-the-shelf vane or a cup anemometer to be able to plug into the simple flow equation and directly measure the velocity. However, I'm discovering some of the things that went wrong in this experiment, or sources of error, I should say. One of them is this non-uniform velocity field. So you have no slip boundary conditions along the walls, and you create a velocity field that isn't the same, which has an effect on the way the blades spin in the anemometer, the vane anemometer, and then give you potentially incorrect readings, which is one of the reasons that the size of the anemometer and its comparison to how big the duct is important. And in some of the bench scale experiments we did, we weren't conforming to the EPA rules, and I think that's a source of error for us. Also, there's some upstream anemometer effects. You'd expect downstream effects of putting the anemometer in the airflow, but there actually are some upstream effects as well. So looking into that and the error that causes in our measurement. Wet versus dry conditions, not having well-mixed CO2 on the bench scale experiments. There's variation in the CO2 levels across the vent where that isn't a factor in the actual Panda Express vent. I've also been looking into this conditional bivariate probability plot. Basically, it expands on this method for source detection, conditional probability function most people have heard of, where you're binning the wind direction with respect to concentration, in essence. And this open air, you've seen this plot before, but this open air coding or presentation tool in R, visualization tool, I should say, in R, uses bivariate data, so wind speed and wind direction, and it helps give information about the dispersion characteristics, which will allow us to then integrate the Gaussian plume methods from this is kind of the generally accepted way to find maximum concentration from a source. And so using these in conjunction with what I've learned about Gaussian plume methods, I think will be a good way to further the research with respect to source quantification, where there really isn't a lot of literature out there yet. So that's the general overview. Thanks.